Good afternoon, everyone. Hope you're having a great time at London Summit today. Can everybody hear me okay? Couple of thumbs up, good. I hope you're having a great day. If you haven't checked out some of the cool activations and games that we've got, I definitely recommend for the 80s and earlier babies amongst you, go and check out the Gladiator Style Travelator. It's really, really fun. We were definitely battling to get on that one this morning. But today I wanted to start with a little bit of a survey, if you don't mind. So for those of you who are sitting here, I'm assuming that you are engineers, architects, SRE, DevOps, platform operators of some sort of shape or size. And if you're not already, or maybe you have previously, you'll be supporting some sort of IT system or application. So I wanted to survey you quickly and ask, of those of you supporting a system today or previously, how many of you know what the utilization or user demand is on your system at, say, 11 a.m. tomorrow? Right, hands up. Okay, we've got a few shy hands. That's good. And of those people with their hands up, how many of you know what that utilization or demand looks like in 6 months from now? So 30th October 2025. Okay, almost no hands. And does anybody know what the utilization of those systems might look like in, say, 5 years from now? So 30th of April 2030. Almost no hands. Good. Now, these aren't trick questions. I'm asking these questions because this stuff is hard. Predicting user demand and utilizations of our systems are difficult. And it's difficult because the pace and the rate of change today in our systems is so great. The systems that we build today will not look the same tomorrow. So they're not going to look the same in 6 months from now. And they may not be consumed in the same way as they are today. They may be consumed by a different system or using a different device or an interface or a different client. And the reason I'm asking you about demand and utilization is because it has a direct impact on how we scale our systems. And as I've mentioned, that this is hard sometimes to determine for our systems. So what if we change the question? So the question is no longer, what is the user demand on my system at arbitrary date in the future? What if the question becomes, how do I build a scaling system that can respond in a super, super speedy manner in a way that's efficient and cost effective? My name is Natasha Wright. I'm a container specialist here at AWS, and I'm working with customers implementing container-based systems who are trying to answer this exact question. Today, as well as from me, you'll also hear from my colleagues, Islam, who is a solution architect at AWS, who'll be stepping through how we might answer this question with Kubernetes. And finally, I'm delighted to say we'll have Dan Massey, who's VP of Architecture at 10x Banking, who'll be stepping through how 10x answer that question for their customers. So for those of you supporting systems today or have supported systems in the past, you might be thinking, is the best approach to scaling and the speediest approach to scaling just to pre-scale, just to pre-provision some capacity? And where you understand the demands of your users and those utilization patterns, yes, absolutely pre-scale. But there are some downsides to pre-scaling. And I just want to step through a simple pre-scaling scenario, if you will. So let's imagine we have one user on our system and we have some pre-provision capacity, and that one user is generating an amount of utilization on our system. And that's this nice little green icon here. I hope you at the back can see it and it's clear. And if we double the amount of users using our system, we increase the utilization on our pre-provisioned capacity or pre-provisioned compute. And we start to see that utilization increase. We can see some more green across a couple more of those servers there. And we double our utilization again, double our users again. And we now have all of the capacity that we've provisioned in use and being used. And let's imagine that these users here are, maybe they're shoppers, maybe they're consumers, and they've all logged on to Amazon.com for the deal of the day. They've made their purchase, and now they're logging off. So now we have no users, but we still have our pre-provisioned capacity. So some of the downsides here, or not downsides, but some of the considerations, if you like, for a pre-scaled approach is that we have a lot of idle compute. If we think about stage 1, 2, and 4, we've got compute that we've provisioned, that we're paying for, that isn't necessarily generating us any business revenue. We've then got compute which is unevenly consumed in scenario 2, where we saw some usage across servers sort of 1, 2, and 3 there, but maybe we didn't need to size those servers in the way that we did. In scenario 3, we saw our max number of users in this little story here, and we saw the capacity that we had maxed out. And we all know with IT systems, when we run them at their max, we sometimes start to experience performance degradation. So if we imagine these consumers trying to get the Amazon.com deal of the day, and they experience some performance degradation, that may impact their experience. And finally, with the compute that we're provisioning, we need to make sure that we're looking after it. We need to make sure we're patching it, we're maintaining it, and we're securing it. And that comes with a cost to us as operators and SRE and DevOps people. We need to spend time and effort actually maintaining and looking after that compute, maybe even in scenarios as in scenario 4, where it's not being used. So let's think about what this spike in user demand looks like in the Kubernetes world. So if you're using Kubernetes with AWS, you're likely using Amazon EKS or our Elastic Kubernetes service. And for your data plane, you might be using EC2 instances. So let's imagine you've made a deployment to your cluster. So you have your containerized workload, which is deployed, and it's been scheduled by our Kubernetes scheduler on an EC2 instance. So that looks a little bit like this. And let's think about a user demand now. So if we have a user curve that looks a little bit like this, perhaps this is something like a timesheet system that you might have in your organization where everybody has to log their hours before the end of the week. You might get those early birds who log their hours on a Thursday night or a Friday morning, but in reality, everyone's going to do it 10 minutes before they go home on a Friday. But that workflow or that user demand is actually quite predictable. So let's think about something that's quite unpredictable. What if perhaps there's been a social media headline about when the next James Bond film is going to be released? So all of the diehard James Bond fans suddenly rush to log into their bank account to make sure that they've got enough pocket money so that they can pre-purchase tickets from their local theatre or cinema. So actually, this user curve is now representing the demand of our diehard James Bond fans. So we have our super keen fans right at the beginning, so that's the left side of this picture. And at first, we have enough capacity in our Kubernetes-based workload to handle the demand of those James Bond fans wanting to log in to check something in their account. But as the news is leaked and more people know that a film is about to be released, we start to see a spike in user demand, and we need to scale. So we need to scale this workload on our Kubernetes cluster. And whether that is a manual scale or an automated scale, we know that we need to scale by adding some additional pods. So we need to increase our pods in this scenario here by 4. So we're adding additional replicas for our particular workload. So we now take some time to ingest, I suppose, that demand signal and react to it. But the Kubernetes scheduler doesn't have any compute in this scenario to schedule these pods. So we need to increase the amount of compute, or in this scenario, the number of EC2 instances in our environment. So we now need an additional 4 EC2 instances, because with this particular cluster, I've made a decision that it's a one-to-one mapping between my workload pods and EC2 instances. But I still don't have my pods up and running because I now have to start up those EC2 instances. And that's not just bootstrapping an instance to your control plane and waiting for that to become available for the Kubernetes scheduler. You may have other scripts or activities that your EC2 instances do in your AWS account when they start up. We see lots of customers have user data scripts where they execute custom scripts for their particular environment. So we need to wait for our nodes to start up. And it's only once our nodes have started up that then our pods can actually start up. Now, this takes time as well. If we think about perhaps a Java application or maybe an application that loads a lot of data into cache or in memory, there is also a startup time there as well that we need to consider. And finally, once this has happened, we have enough capacity to satisfy all of our diehard James Bond fans. But it's only really at this point in time that we have enough capacity to satisfy that demand. And if we think about when the James Bond input signal came in to the end, we can think of this really as our scaling latency. Or for our James Bond users, this is kind of a cost to them, if you like, of scaling. So what we really want to happen is each of these stages of scaling, so gathering that input signal, our node starting up and our node scaling, and then our pod starting up, all of these stages are stages that we want to optimize, and not just for speed to handle our greedy James Bond fans that really want to move quickly, but also the efficiency and scaling with cost optimization in mind. So these are all things that we want to consider when we think about scaling. So that's a little bit about the problem and why we want to answer that question of how do we build great scaling systems. So Islam, you work with Kubernetes customers all the time, and how do you propose that they solve this particular problem and this particular question?
Let's take a... Hi everyone. Can you hear me okay? Okay, good. Okay, great. So now you know that scaling Kubernetes and scaling workload in Kubernetes is an involved process. You need to optimize it for performance and for cost efficiency as well. You want to reduce scaling latency as much as you can, and you also want to make sure that you have minimal idle resources or underutilized resources. So in the next few minutes, we are going to talk about different tools that you can use to optimize and achieve these two objectives: reducing node scaling and pod scaling latency, and also achieve higher cost efficiency. First, let's start with a quick refresher on scaling workloads in Kubernetes. In Kubernetes, scaling happens at two levels. The first level is the pod level, and the second level is the node level. At the pod level, you have an application. This application is running inside a pod. And let's say you are receiving increased amount of traffic for this application. One way to respond to this is by adding more application instances. In other words, add more pods running the same application. This is horizontal autoscaling, and you can achieve this with horizontal pod autoscaler, HPA. This is the capabilities that you get by default with Kubernetes. You don't need to install any additional controllers to get that. And it allows you to scale in and scale out your pod based on CPU or memory utilization. The other option you got is to vertically scale your pod. And by that, I mean make it a bigger pod. So you can allocate more CPU or more memory to your pod. And this can be achieved with vertical pod autoscaler, or VPA. Unlike HPA, VPA is a separate project that you need to install yourself into the cluster. Sometimes CPU and memory are not the best resources for you to scale based on. Think of a worker service that is processing messages from a queue. You can better scale this service based on the queue depth. This will give you a more responsive scaling mechanism compared to waiting for CPU utilization to pick up, and only then you scale out. KEDA, which stands for Kubernetes Event-Driven Autoscaling, can allow you to scale based on events, like increased queue depth, rather than scaling based on CPU and memory utilization. Now you scaled your pods, so you have created more pods, or you have made your pod a little bigger. You need to increase your EC2 capacity to accommodate this increased number of pods or bigger pods. And that is where node scaling comes into the picture. Traditionally, we have been using cluster autoscaler to scale the underlying nodes. Cluster autoscaler has a concept of node group. Under a node group, you have fixed size nodes. If there are pods that are bending scheduling, the cluster autoscaler will provision one of these worker nodes of these fixed sizes, even if it is a tiny pod, and you may end up with some cost inefficiencies. In addition to that, cluster autoscaler depends on EC2 autoscale group. What this means is you got more than one controller involved in the scaling process, and this can add to the scaling latency. An alternative for cluster autoscaler is Karpenter. Karpenter is an open source project. It is built by AWS and donated to CNCF. It's high performance autoscaler. It doesn't require or doesn't depend on EC2 autoscaling group, which means there are less controllers involved, so less latency in the node scaling process. And also, it doesn't have this concept of node group. Actually, it calculates the total capacity required for the pod spending and scheduling, and accordingly decide the EC2 instance type that is suitable for these pods that are bending and scheduling. Little bit deeper dive into HPA, horizontal pod autoscaler, and vertical pod autoscaler. This is how the flow looks like for HPA. You have a controller. This is a HPA controller. And you have the metric server. And the HPA controller is continuously retrieving CPU and memory utilization for pods from the metric server. And based on the autoscale policies that you put in the HPA object, it aggregates all these CPU and memory utilizations that are retrieved from the metric server, and then compares this with the target utilizations that you put in the HPA object, and accordingly adjusts the number of pods in your deployment. And this is how the pod horizontal scaling happens. VPA is slightly different. So VPA is, again, the same like HPA in terms of retrieving these metrics from the metric server. But when it comes to the response it takes to that, it actually either changes the CPU and memory requests that are made by the pod, or it make a recommendation to you for these new values based on the actual consumption of the pod. Bear in mind that when you are changing the requests that are allocated to your pod in terms of CPU and memory, this will typically lead to a restart of your pod, which can lead to a disruption. That's why many customers, when they use VPA, they use it in this recommendation mode, just to get some recommendation and accordingly fine-tune the CPU and memory allocated to the pods. There's a new feature in Kubernetes. This was graduated to beta in 1.33. This is an in-place pod resizer. It allows you to change the resources allocated to the pod without a restart. Once this feature is GA, it will become available in Amazon EKS, and then you can use it, and you can use vertical pod autoscale to change the requests without worrying about the pod restart and the disruption it may cause. Now we'll talk about KEDA a little bit. So KEDA gives you this alternative for pod autoscaling, which is based on events rather than being based on CPU or memory utilization. It comes with 70 plus built-in scalers. These are scalers for different platforms. So there are scalers for AWS. There are scalers for other platforms as well. In AWS, you can scale based on Amazon SKS, Q, depth, or you can scale based on DynamoDB table and many other services. These are the different scalers that you get with KEDA. KEDA works alongside HPA. What this means is under the hood it is using HPA. It's not reinventing the wheel. What it does is it consumes this event information from these different built-in scalers and then make them available in the form of a custom metric. And these custom metrics are then used by HPA controller for scaling. A key capability that you get with KEDA is the ability to scale down to zero. When you are receiving no load at all, then KEDA is able to scale down or deactivate your application. This is how KEDA operates at a high level. The process starts with you creating a custom resource called scaled object. The scaled object, you put in this custom resource the targets that you want to auto-scale, whether this being deployment or stateful set. you also specify the triggers that will lead to a scale out or scale in event. And you also specify the minimum number of pods, maximum number of pods, and a bunch of other things. You apply this scaled object to the Kubernetes API server, and then KEDA controller picks this up. It integrates with different event sources, like the one that I have showed in the previous slides, and it makes the information available in these event sources. It exposes this information in the form of custom metrics to the horizontal pod autoscaler. KEDA autoscaling happens in two phases: the activation phase and the scaling phase. The activation phase, you can, if you have an application or a deployment and this deployment is not receiving load at all, KEDA is able to deactivate this deployment by setting the number of replicas to 0. Once load starts coming in, let's say messages arrive into a queue, then KEDA is able to activate the deployment by setting the number of replicas to 1. Once the activation happens, then the scaling phase takes over, and the scaling phase is responsible for scaling in and out your deployment from 1 to n number of pods. And this is totally taken care of by HPA, but based on the custom metrics that got exposed by KEDA. This is how, this is just an example for a scaled object. You see here we have targets that we specified in the object. We have also specified the polling interval. This is an important configuration because if you want to implement this responsive scaling, you may want to reduce this polling interval. The idle replica count is another important configuration. Here we are specifying how many pods we want to have when there is no load at all. So if you want to scale to 0, you just set this to 0. And then you specify the triggers. Here, in this case, the trigger is the number of messages that are pending in an SKS queue. Sometimes we know ahead that we are going to have an event at certain time, at certain point, right? So the best scaling mechanism to have in this case is a scheduled scaling. So you know ahead that there is a certain event that will happen at this specific time, and you know that this is a load that you should expect. Then what you can do is you define a scheduled policy, a scheduled scaling policy, and you can do that with KEDA. The trigger in this case will be of type cron, and you can specify the start time, the end time, and the number of replicas that you want to have during this event. Now you have scaled your application, you have scaled your pods. Let's talk a little bit more about node scaling. Karpenter is the alternative that I spoke about earlier. It is an open source project. It is a Kubernetes native. You can configure it using simple custom resource. It's also node groupless. What this means is it doesn't have any dependency on an EC2 autoscale group. It doesn't have this concept of node group. So there is no additional controllers that add latency to the scaling process. Also, it has this automatic node scaling feature. Automatic node sizing. What this means is Karpenter is able to calculate the aggregate capacity of all the pods that are pending scheduling, and accordingly, it decides the EC2 instance type it provisions, and save you cost and prevent use cases where you end up with large amount of underutilized or unutilized capacity. It's high performance. What this means is it really provisions and deprovisions node quickly. If you are recently switching to Karpenter, you will notice a considerable difference when it provisions nodes based on pending pods. This is how Karpenter works. So in our case, let's say we used KEDA for pod autoscaling. So KEDA provisioned a bunch of pods, and these pods are now pending scheduling. Previously, before Karpenter, and if you are using cluster autoscaler, the cluster autoscaler will kick in, will identify that there are no pods, that new nodes need to be provisioned to accommodate these pending pods. And it will increase the number of instances for the corresponding EC2 autoscale group. And only then the autoscale group will be able to provision a worker node, and the pending pods will get scheduled into that. With Karpenter, we are able to replace these two controllers, the autoscale group and the cluster autoscaler, with Karpenter, one controller. The way you configure Karpenter is through a custom resource, which is a node pool resource. You see it here on that slide. There are different configurations that you put in the node pool. You can specify the instance families that you want Karpenter to consider when it is provisioning EC2 instances for scheduling your pods. You can specify the number of CPUs that you can be more prescriptive in terms of the number of vCPUs. So you can say only provision EC2 instances with at least 4 vCPUs. You can also specify the AZs, or the availability zones that you want these worker nodes to be provisioned in. You specify the architecture if you have specific requirement for that. So you can say I only want x86 architecture, or I want ARM architecture. You can also specify the capacity type, whether you just want to use on-demand, or you want to use spot instances, or you want to use spot and fail back to on-demand if spot is not available. You can also put limit in terms on the CPU utilization, or sorry, not the CPU utilization. You can put a limit on total number of vCPUs that are provisioned by Karpenter. You can decide whether to use just one single node pool, and this is used for all your workloads and different teams, or you can go for multiple node pools. And in this case, you have separate pool of node for different teams and for different workloads. One of the important features of Karpenter is the consolidation and the continual optimizations. Karpenter is able to continuously check the EC2 instance fleet that you have and reduce and try to shrink it as much as possible. So in this case, Karpenter is able to identify that the two EC2 instances at the right-hand side can be terminated, and can be actually the pods running there can be scheduled into the second node on the left, like you see here. You need to specify in the node pool that you want it to be consolidating based on empty, whether the EC2 instances are empty or underutilized. This is another scenario of consolidation. In this case, Karpenter is not able just to terminate EC2 instance, but is able also to replace these EC2 instances with a smaller one that is just big enough to accommodate the pods that needs to be scheduled. So it is terminating one instance, replacing the other with a smaller one that is big enough to accommodate the pods and save a little bit more capacity. Karpenter is able to consolidate. This is done very efficiently with the Karpenter controller. It aims to reduce the overall EC2 capacity. And it does that by trying to fit your pods in a smaller EC2 capacity, while respecting your pod constraints and while your scheduling constraints and your node constraints. It's important to know that Karpenter is not able to consider or examine all different consolidation scenarios. Sometimes there are just too many consolidation options for Karpenter to examine. So what it does is it follows certain heuristics to implement this. The objective is to reduce disruption as much as possible to workloads. So to do that, it picks or gives preferences to worker nodes that are running fewer pods, or worker nodes that will expire soon, because they will expire soon. So it prioritizes it in terms of consolidation examination. And lastly, it also prioritizes nodes that are running low priority pods. Generally speaking, there are two types of consolidation that can happen with Karpenter. The first is called N to 0. N to 0 means we are just replacing n number of nodes with zero nodes. So we're just terminating these nodes. And here's an example for that. So these different rectangles are nodes of different sizes. What Karpenter will do in this case, it will figure out that it can terminate the two nodes at the top and the bigger one beneath them, and these pods can be scheduled into the remaining worker nodes. So this is N to 0 consolidation scenario. The other one is N to 1. In this case, we are replacing one or more worker nodes with just one worker node, which is in capacity less than all these ones that are being consolidated. And here is an example for that. So these are two worker nodes that are not fully utilized. Karpenter is able to replace these two worker nodes with just one worker node, which is big enough and just big enough for accommodating all the pods that were running on the two previous nodes. Now let's see how 10x Banking used Karpenter, KEDA, and other open source projects to make responsive auto-scaling and more cost-efficient implementation. I would like to introduce Dan Macy. He's going to the VP of Architecture at 10x Banking, and he's going to walk you through that. Thank you.
Can everyone hear me? 10x Banking is a cloud-native core banking platform for financial institutions and their partners. Founded by former banking executives and built by technologists, 10x Banking platform offers customers best-in-class security, scalability, and speed. Proven through transformational deployments with Westpac, Chase, and Old Mutual, 10x Banking offers banks the fastest, most cost-effective, and de-risked path to full cloud-native transformation through its unique micro-core approach. Its scalable, resilient, and flexible technology is built to empower financial institutions to better serve their customers and their communities. 10x Banking comes with the world's most powerful managed core and a rich layer of pre-built product fundamentals. These allow customers to focus on their high-value customization and localization. Interoperable by design, the 10x platform is ready to be extended in any programming language, from .NET to Java to Python, and is API ready for integration into customers' ecosystems. The 10x platform is deployed in Kubernetes, either as a managed SaaS or self-hosted, depending on what's best for the customer and their circumstances. It's built with a microservice architecture with Java and Go-based services, with PostgreSQL as a database and Kafka for events. At 10x, we have realized several benefits of using Karpenter and KEDA. Karpenter has allowed us to make efficient use of spot instances by allowing us to always use the cheapest available that meet our criteria. We've been able to reduce the cost for non-production environments. Karpenter's also allowed us to have better node utilization. Through its consolidation and disruption policies, we're able to periodically consolidate low-utilized nodes and result in fewer EC2 instances running at any particular time. While KEDA has allowed us to scale on factors other than CPU, which means that we can make scaling decisions faster than ever before. We do still, however, have several scaling-related challenges. Sporadic use of our non-production environments means there's lots of idle compute when they're not in use. This leads to higher cost by having these environments always on and ready to serve requests. We can address both of these if we're able to scale to zero. However, by doing so, we have to address the full time it takes to scale, because the end-to-end process has to be optimized at every stage. I'm going to show you how we've tackled these challenges at 10x and realized the benefits of scaling to zero. At 10x, we have two types of microservice: online transaction processing services, or OLTP, and asynchronous event-consuming services. OLTP services handle customer requests synchronously, persisting results in the database, and events end up in Kafka. And the second set of services consume those events. Both types of services should be capable of scaling independently on the factors most important to those services. In our experience, CPU utilization is not an effective measure to scale OLTP services on. It's far more effective if we're able to scale based on concurrency. If, say, our service is known to handle 1,000 requests a second, we should be able to scale up well before we get to 1,000. And the KEDA HTTP add-on enables us to do this. The KEDA HTTP add-on acts as a proxy, and it maintains an internal metric of the concurrency and throughput going through that service. That means it's able to make real-time decisions on when to scale, informing KEDA to scale up and add more pods to our service. After scaling to zero, because all the traffic's going through the KEDA HTTP add-on, it's able to buffer those requests until a new replica is able to come up. Similarly, KEDA has been used to scale our asynchronous services. Rather than scaling in CPU, A better indicator for event-consuming services is the scale based on the number of events waiting to be consumed and how far behind we are. The Apache Kafka scaler enables us to do this with Kafka. It's able to monitor a proxy metric such as consumer lag and scale when the queue becomes too big. This also enables such services to scale to zero, because when there are no further events to consume, it scales down, and when there are further events, it scales back up. KEDA's allowed us to scale in the right circumstances. However, in order to scale to zero, we must optimize the entire flow, so we can scale back immediately when it's required again. Natasha and Islam have already spoken around how we can optimize the cluster scaling and the pod scaling. And that's making the scaling decision really quickly. But after we make that scaling decision, there are a number of factors that come into play that leads to longer times to actually scale out. All of these are important to be optimized, all of them add into the overall end-to-end time. And as examples, these include things such as the time it takes for an EC2 instance to be considered ready by Kubernetes. So the time it takes for all the admission controllers in the cluster to perform their validations and their mutations. The time it takes for the number of sidecars and init containers you've got to become ready. All of these take time. We have found, though, that most time ends up being spent waiting on the cluster scaling, the image pull time, the application start time, and then the time for the pod to become ready for Kubernetes. Let's look at how we've addressed these at 10x. While Karpenter solves the problem of scaling nodes quickly, it's still not fast enough for scaling to zero. We have to scale up instantly. We really have to be able to decouple the application scaling time from the cluster scaling time. And one approach to do this is take advantage of pod priority in Kubernetes. Pod priority indicates the importance of one pod compared to another. And in the example where you have a high priority pod waiting to be scheduled, and it can't be because there's not enough capacity in the cluster, the kube scheduler will deschedule a low priority pod to make space for it, so the high priority one can be scheduled immediately. That means that we defer the cluster scaling process to the rescheduling of the low priority pod. By using a deployment of low priority pods, we essentially over-provision some capacity in the cluster that's shared across all resources. And that's a trade-off. It's a trade-off between the extra cost for those low priority pods and the overall time to scale, where we get overall benefit of reducing the overall cluster cost. So once a pod is scheduled, the next thing we have to look at is how do we get the containers it needs onto the nodes as quickly as possible. And typically you're pulling your images from a remote registry, and that can take tens of seconds. The bigger the image, the longer it takes. If we're able to use images from the node itself, we can reduce that time to milliseconds, and one approach to achieving this is to make use of a daemon set. With a daemon set based approach, we specify all the images that we need in the cluster as part of that daemon set. It means that when a daemon set pod is scheduled on a node, it pulls all of the images from the remote registry, it caches them in the local node. And then when we have another pod coming in, rather than pulling from the remote registry, it pulls from the local cache. And that happens in milliseconds. Thereby, we avoid all the network transfer, we avoid pulling it from remote registry, and we really speed up that process. So once we've scheduled the pod onto the node quickly, we have to look at how quickly can we start the application. And at 10x, we have a lot of Java services, and Java services can be very slow to start, particularly when we're using frameworks that have got lots of dynamic configuration at startup time, and when we're running containerized environments, when we're constraining and managing the resources allocated to them. One approach to optimize the Java startup time is to use an OpenJDK feature called Coordinated Restore Checkpoint, which we call CRaC. CRaC enables instant startup times of Java, and has support built into most of the Java frameworks. With CRaC, we build our application as normal in our CI process and put it in a container, but then we start it up. We then warm it up with some requests, and at this stage, we're doing all the kind of Java tiered compilation levels. It's done its dynamic configuration, it's warmed up, it's fully optimized, ready to go, depending on the extent of your tests that are running against it. We then take a snapshot of that warmed up application, and that snapshot is stored in a new container that we store in a remote registry. And then when it comes to running the application in Kubernetes, we start it up, we restore that checkpoint, and it's immediately available to serve requests. It doesn't have any of the tiered compilation to do, it doesn't have the CPU spikes, it's just good to go. Now, CRaC does come with some configuration challenges, but for us, we've been able to overcome the cold start issue. We've also benefited from a lower memory footprint, and we've avoided the CPU spikes that we previously had. So once we get the application ready to go, we really need the readiness probe to pass as quickly as we can. If the application is capable of starting in less than a second, we want the readiness probe to pass in as close to that as possible. With a standard readiness probe, it's got a period of 10 seconds. And the first time that readiness probe runs, it's going to be immediately, as soon as the application is ready, it'll fire it immediately. Or in fact, as soon as the pod's scheduled, it'll fire it immediately. And that could be too fast. Your application may still be coming up, even if you've got it as a sub-second start time. You've then got to wait for another 10 seconds before the probe will be tried again. What we can do is pick a shorter period. We could try it every second. So it means if you've got a second period, it'll be ready in a second. However, that means that we're polling it every second for the duration of the lifetime of that pod, which can be far too much. An alternative to this is to make use of a startup probe. A startup probe allows us to poll every second to start with, to make sure that we get to the point where the pod is ready. And then our readiness probe is able to use the default settings and poll at a more reasonable number. So after putting all of these optimizations together at 10x, what have we achieved? We've reduced our end-to-end scaling time from over a minute to a couple of seconds. We've reduced our application startup time to less than a second, and we've achieved this using CRaC and all the other optimizations I've spoken about today. And for the services where we have applied these optimizations and been able to scale to zero as a result of that, for these services we've been able to realize a 40% cost reduction, both in compute and observability costs. So from today's session, there are three key takeaways. First, we've seen that resource-based scaling is limited, and it results in degraded performance for customers. Alternative to this is to make use of KEDA. And KEDA comes a wide range of scalars, where we can scale in the factors that are most important to your application. We've seen that Karpenter is a high-performance cluster autoscaler, which results in better node utilization and cheaper clusters. And finally, I have shown how 10x Banking has made use of these technologies and further optimized the whole end-to-end scaling process to realize the benefits of scaling to zero.
Thank you very much, Dan. So I'd like to challenge everybody to test out KEDA with Karpenter. We have a really good sample on our AWS repo on GitHub, which is a really great quick start guide to build you an EKS cluster with Karpenter and KEDA. So I challenge you all to also achieve sub-second application scaling and startup time. If you could please fill in the survey, that would be wonderful. And we'd like to say a huge thank you to everybody for joining our talk today. And if you have any questions, we will be hanging around at the front in case you're interested in discussing anything we've seen today or talked about today. So thanks, everybody. Have a great summit.